In a prior screencast, we analyzed a fin in which the temperature of the base of the fin was known, and we assumed that the tip of the fin was adiabatic. In doing so, we came up with four main things. We came up with the temperature profile, first off, and then we figured out what the flow of heat was through the base of the fin, and then we figured out what the hypothetical maximum flow of heat could be through the base of the fin, in the limit in which the thermal conductivity of the material goes to infinity. And then finally, we talked a little bit about what a fin efficiency, which is the ratio of the actual amount of heat being drawn through the base of the fin divided by that hypothetical maximum. Now I want to talk about the flow of heat not only through the fin itself, but the flow of heat also coming from the base, because after all, you probably have something hot on the other side of this base, and your goal is to remove as much heat as possible no matter how we do it. So we want to figure out, we've got heat flowing from the base, and then we've got heat flowing into the base of the fin and then outward. So we'll want to think of this in terms of a resistance network, because we're going to have two resistances in parallel. The resistance due to convection directly from the base, and the resistance due to convection from the fin. When we set up a resistance network, we're usually looking for a driving force, a temperature difference divided by a total resistance. In the case of heat removal from the base itself, the resistance is fairly straightforward to formulate. The resistance of the base is just equal to 1 over the heat transfer coefficient multiplied by the area of the base. But it's a little bit trickier for the fin, because what temperature do we use as the driving force? Because the temperature out far away from the base is much cooler on the fin than it is at the base. So to do this, let's work with our thermal efficiency. So we can rewrite that. We could say that the heat being removed from the fin is equal to the fin's efficiency multiplied by the theoretical maximum rate of heat transfer from the fin. And that's going to be equal to the maximum heat transfer will be equal to H times A times the assumption that the temperature of the fin is at the temperature of the base everywhere minus T infinity. Where here the area is equal to the area of the fin, and we can rewrite that as the perimeter times the length. We could also write this in terms of the driving force, Tb minus T infinity, divided by the resistance of the fin. And in doing so, we can now show that the resistance of the fin equal to 1 over the fin's efficiency times the heat transfer coefficient times the perimeter times the length, which is just the area of the fin. And when we compare this to the resistance of the base, which is just 1 over H times the area of the base, we find that the fin's efficiency is almost like a correction factor. So now, instead of considering just one fin, let's consider an array of fins. So here I've made a model in which I've got 79 different cylindrical fins sticking out of the surface. So for the sake of this analysis, let's assume that the fins are perfectly bonded to the base. I've only changed the color just to differentiate between the two areas that we need to consider. The first area being the area of each individual fin, which is what we've defined before, and the other area that we're interested in is the area of the base itself. So let's take a look at our array from two different perspectives. So in our instance, we know what the temperature of the base, and we know the ambient temperature T infinity. We have some idea of what the heat transfer coefficient is. So the two things that we're going to deal with, let me dimension our base. In this case, it'll be a square with dimensions A on both sides. And let's see, so the area, we know that the cross-sectional area of each fin, and we're trying to figure out the area of the base, which is just equal to the total area, A squared, minus N, the number of fins, times the cross-sectional area of each fin. In this case, I've got a 7 by 7 array, so I've got a total of N equals 49 fins. So let's set up a resistance network. If we look at this, there's going to be a total of 50 different ways for heat to move from the base into the ambient air. So we've got 49 different fins and then the base itself. So let's write a resistance network. So we'll call this the temperature of the base, and then there's going to be 49 different fins. So I'm just going to call this R1 for the resistance of the first fin, R2, the resistance of the second fin, all the way down until we hit the resistance of the 49th fin. And then our final resistance in parallel is the resistance of the base. So heat can flow through the base or one of 49 different fins and out into T infinity. Because we're dealing with 50 resistances in parallel, we'll write our total resistance as shown. So let's try to simplify this a little bit. We can take all of the fins and we're going to combine them. We'll just say that this is the number of fins divided by the resistance of each individual fin, because R1, R2, all the way through R49, it's the same expression. They're all identical fins. As we established, this is the resistance of one individual fin. We're just going to combine all of these together and say that this is equal to 1 over the resistance of all of the fins are fins. We know the resistance of a single fin is equal to 1 over eta times h times the area of the fin. Rearranging our fins is equal to the resistance of a single fin divided by the number of fins. So the resistance from the total fin is just equal to 1 divided by the number of fins multiplied by their efficiency multiplied by the heat transfer coefficient times the area of each individual fin. By doing this, we've made our life a great deal easier because we can just say that the heat either escapes from the base or it escapes from the fins, in which we'll use this resistance, a total resistance for all of the fins. And this is what our simplified thermal circuit looks like. We either got heat flowing through the fins or heat flowing through the base. So our total rate of heat transfer then, Q out, is equal to the driving force, the temperature of the base, minus the ambient temperature, divided by the total resistance, in which we've defined our total resistance now as just two resistors in parallel. 1 over R fins plus 1 over R base, the reciprocal of those two sums. And when combined, these equations form a fairly convenient way to calculate the total rate of heat transfer from a fin array.